Hello, I'm Mauricio Salerno, and I'm going to be presenting a joint work with Raquel Fuentetaja titled Elimination of Unnecessary Actions from Plans using Automated Planning. We all know that planning is hard, but there exist satisfying planning approaches that can solve large problems relatively fast. The problem is that these solutions can be far from optimal, and in some cases the plans found can even contain unnecessary actions, which are actions that can be removed from the plan and still get a valid plan. These unnecessary actions can be identified and removed in a post-planning optimization step, but the problem of eliminating all the unnecessary actions in a plan is known to be NP-complete. In this work, we try to encode this problem as an automated planning task. As motivation, we ask ourselves what makes a plan a good plan. We typically think of a cost function. The lower the cost, the better the plan. But quality could also be related to the usefulness of each action in the plan. For example, actions that can be removed from a plan while maintaining its validity are not justified. And this idea of analyzing the usefulness of actions is known as plan justifications. It was first formalized by Fink and Yang in a work where they defined three types of plan justification: backward justification, well justification, and perfect justification. We are going to focus on perfect justification, which is the strongest of the three. And basically, we say that a plan is perfectly justified if it does not contain a valid proper subplan that solves the original planning task. Again, verifying if a plan is perfectly justified is NP-complete. As an example of a plan that is not perfectly justified, we have a blocks board task where initially all blocks are on the table, and we want to get to a state where block B is on top of block A. The plan we have is to pick up C, put C on top of D, then pick up B and stack B on top of A. We can clearly see that if we remove the first two actions, we get a plan that is valid because each action is applicable and we reach the goals. So these two actions together are not justified. They can be removed and still get a valid plan. So this plan is not perfectly justified. Formally, we define a perfectly justified plan as one where all the subsets of its actions are well justified. And a set of actions, a subset of actions of a plan is well justified when the removal of said subset of actions creates a plan that is not valid for the original planning task. With the idea of perfect justification, we can try to find the best perfectly justified subplan given an input plan. These problems are known as the minimal length reduction and the minimal reduction problems. The minimal length reduction problem tries to eliminate the maximum number of actions from a plan while still getting a valid plan for a task. And the minimal reduction problem tries to find the subplan with the least cost by eliminating action from the original plan. So we want to solve the perfect justification problem using automated planning. So as input we have a planning task and a valid plan for the task, and we want to define a new planning task pi prime where any valid plan for this new task is a subsequence of actions of the original plan, and this new plan must also be applicable from the initial state, and it must reach the goals in the original task. To do this, we define the pi-skip planning task, where we modify the set of facts of the task, the set of actions, the initial state, and the goal state remains the same as in the original task. We modify the set of facts by adding three new sets of facts. The first one is last, which is used to encode that the last action considered in a state is the ith action of the original plan. We have now the fnext facts, which basically encode that position 1 comes exactly before position 2 comes exactly before position 3, and so on. And a set of facts called plan action, which just encode the fact that one action appeared in the original fact. With this, we modify the original state by adding the fact that so far we have not considered any actions from the original plan. We encode all adjacent positions in the original plan, and for each action in the plan, we encode the fact that action A appeared in position I in the original plan. Now for the set of actions, for every action A in the original plan and in adjacent positions in the plan, we define a new action where the preconditions of action AJ are the original preconditions of the action joined with the fact that an action A must have appeared in position J in the original plan, that the last action considered so far was action A, and that action J comes immediately after action I in the original plan. The add effects are modified to say that now the last considered action is action J, and we delete the fact that the last considered action was action I. We also have a set of skip actions, which basically skip actions from the original plan or eliminate them. The preconditions to skip action J is that the last action considered was action I, and we know that J comes after action I in the original plan. Now to skip J, all we have to do is say that the last considered action is action J, and we delete the fact that the last considered action was action I. As an example of how the compilation works, we have the same blocks problem as in the example, and we have a search tree showing what the compilation would look like. Originally, we know that we haven't considered any actions in the original plan, and we have all the facts in the original initial state. Now, the only thing we can do is either pick up C or skip the first action, which is pick up C. If we pick up C, we now know that the last considered action was the first action and that we are holding C. And on the other hand, if we skip the first action, we know that the last considered action was pick up C, which was skipped, and that the arm remains empty because we didn't pick up C. In this case, since we didn't pick up C, we cannot execute action 2 because we are not holding C, so the only thing we can do is skip it. And if we continue this process, we will eventually find valid plans. On the left hand side, for example, we have the plan where none of the actions of the original plan were skipped, and on the right hand side we have a plan where the first two actions were skipped, and then we only pick up B and stack it on top of A. Now we can clearly identify some actions that cannot be skipped from the plan if we want to achieve the goals of the planning task. If a goal fact only appears in the added effects of one action of the plan, we know that that action cannot be skipped because we wouldn't achieve that goal. And now, since this action is necessary, its preconditions must also be met. In this way, we recursively define actions that can be trivially identified as necessary. With this information, we enhance the compilation. Now we know what actions are trivially necessary and what actions are not trivially necessary. So we add an additional precondition to the skip actions, and we say that in order to skip action J, we have to know that action J is skippable, and we add the skippable facts for every action in the original planning task that are not trivially necessary. We also have another compilation where instead of using skip actions, we define a complete order over the actions of the plan. And in order to execute an action, instead of checking that we know that the last action executed was I and that J comes exactly after position I, we just need to check that J happens after position I, not necessarily exactly after. So now we can skip multiple actions with a single action. So we experiment with these compilations. We try to solve the minimal length reduction and minimal reduction problems. We use the PySkip, the enhanced compilation, and PyOrder compilation, and we compare the results of our approach with a weighted max-SAT approach and a suboptimal greedy approach. to solve the same problems. We use as input instances with plans of the satisfies interact of the 2011 IPC, and we use the fast downward planning system. We measure the amount of cost or length reduction achieved and the execution time. Here we have the results for the minimal reduction problem. The diff column shows the amount of cost that was reduced from all plans. The radio shows the average cost reduction radio for each plan, and the time shows the average time needed to solve each task. As we can see, P-order performed worse than the other approaches, and this happens because the number of facts needed to encode the total order of the actions in the plan is just too large when the plans are long. So the instantiation just takes up too much time. On the other hand, all the other compilations have similar results, solving most tasks in tenths of a second. We also take the PSKIP enhanced compilation and use a satisfying configuration of the fast downward planning system and solve the problems and compare it with a suboptimal approach. Again, the amount of cost reduction achieved is quite similar between the two methods, and the times in most cases are tenths of a second, except for one domain where the greedy approach takes a few seconds and the satisfying compilation we proposed resolves it still in less than a second. As conclusions, we proposed automated planning-based approaches for the perfect justification problems, and we got comparable results to other previous methods. As future work, we want to identify situations where our proposed approaches perform better or worse than other approaches. And we also want to incorporate the notion of plan justifications in settings where it might be relevant, such as top-K planning and plan recognition. Well, this was my presentation, and thank you for your time.